Afternoon, everyone, and welcome to the penultimate talk in our series, Life in the Extreme. Today, we're going off-world with our speaker, Dr. Amy Williams, astrobiologist and assistant professor of geology at UF, whose research focuses on the interaction between microbial life, the geochemical environment, and the rock record on Earth, and how to recognize habitable environments and potentially preserved microbial life on Mars and the outer world moons. Dr. Williams has a PhD in geology from the University of California, Davis, a master's in earth and planetary sciences from the University of New Mexico, and a bachelor's degree in earth and environmental science from Furman University. She has a postdoctoral research associate at NASA Goddard Space Flight Center and has been a member of the NASA Curiosity rover science team since 2009, for which she has received several NASA Group Achievement Awards and is currently working with the Sample Analysis at Mars, or SAM instrument team, to explore the distribution of organic molecules on Mars's surface. She is also a science team member of the more recently launched NASA Perseverance rover, launched in 2020, whose mission is to seek signs of ancient life and collect samples of rock and regolith for return to Earth. She's also informing the next decade of Mars missions as part of the National Academy's Planetary Science and Astrobiology Decadal Survey, where she's been part of a team of 15 Mars scientists who help NASA prioritize missions for 2023 through 2032. Dr. Williams received a nomination for the 2017 Maryland Academy of Sciences Outstanding Young Scientist Award and was a NASA Earth and Space Science Fellow. Recently, she was awarded the 2022 Provost Excellence Award for Assistant Professors. And her talk today to us is The Curiosity to Explore and the Perseverance to Rove, a decade of discoveries on Mars. Welcome, Dr. Williams.
Thank you so much, Paula. It is embarrassing when all of that's read at the same time in front of me, so thank you so much. Thank you all so much for being here in person and online, and hopefully everyone can hear okay and see well, and folks online. All right. Let us know if anything is off. I'm happy to do what we can to fix it. So thank you so much for this opportunity. I do work with Mars missions and I love sharing that with people. And so that's my hope for today, is to give you a little bit of that insight into what the missions are doing and why, and hopefully giving you an opportunity to ask questions that you've always had about Mars and space exploration. And I do feel like an astronaut with this headset, so I'm pretty excited about all of this. I'm waiting for my visor delivery in just a moment. Okay, awesome. So then the final, acknowledgement that I will give is that this is a Prezi, so this is not a PowerPoint. And so a Prezi is a non-linear presentation platform meant for us to be able to explore kind of space, and not just space, but the space within an image, moving in and out of maps. And so what we're going to do is kind of zoom around on our Prezi here. So for some people, it can make you a little bit dizzy if I'm going in and out of images. So I try to do this at a paced level, but I hope you enjoy sort of seeing something that's not a PowerPoint for a little bit here. So let me just jump into Mars exploration and how we got to the point where we are today. As you heard from Paula, I work with the Curiosity and the Perseverance rover missions, but of course we have been exploring Mars for decades now. And so although this schematic doesn't show everything we've done with Mars, this does tell you a bit about what we've been able to explore, at least since the 70s, on the surface of Mars. So Viking 1 and 2 kind of marked the beginning of our surface exploration of Mars from the NASA perspective. Viking was there to characterize the atmosphere, to take images from the surface of Mars for the first time, and notably to search for evidence of life. And now the experiments that Viking carried did not have conclusive evidence for life. It did actually give us so much more information about the surface of Mars, why it's different from Earth, how it's different from Earth, and how we can kind of understand how one of our closest planetary neighbors has really evolved in a very different way from Earth. So we start in the 70s with Viking, we have a bit of a hiatus, and then in the 90s, we start sending landed missions again. This includes the Pathfinder lander with the Sojourner rover, which is this little kind of RC car-sized robot. Now, this was a technology demonstration meant to demonstrate that you could send a little tiny robot rover to Mars, you can operate it, and you can actually do science with it. And this was really the forerunner for our Mars exploration program. In 03 and 04, Spirit and Opportunity, went forward too much here. Spirit and Opportunity, the Mars Explorations rovers here, were sent to follow the water, to find evidence for water on the surface of Mars, which we have now found in a plentiful amount. So that evidence for water is from ancient times on Mars. It's only present now as kind of water ice in the subsurface, a little bit of water in the atmosphere. Every once in a while, some of it melts and you see these little channels of briny water that flow down crater walls before evaporating. And so this is sort of the hydrologic cycle on Mars today. But in the past, it was a really dynamic, warm and wet planet. We have lakes and rivers and glaciers, outflow floods, all of this really incredible dynamic environment that we only see kind of the fossils of today, just this ghostly evidence. So I don't mean to skip our lander colleagues here, Phoenix and InSight, which have given us so much knowledge about the surface of Mars, but sticking with our rover story, in 2011, the Mars Science Laboratory rover Curiosity landed and started searching not now for water, but for organic carbon. So those are the building blocks of life as we know it. We wanted to understand, is there organic carbon on Mars? Could it have fed into an ecosystem very early on? And so Curiosity is actually still running 10 years later. And in 2020, we launched the Perseverance rover. Now, Perseverance is taking that next step from searching for organic carbon to searching for evidence of ancient life on Mars. So we're starting to make this grand circle back to the original intent of Viking to search for our nearest planetary neighbors. So Perseverance is, a year and a half, almost 2 years into our prime mission. And what's really important about Perseverance is that it's able to collect samples for eventual return to Earth with the Mars sample return architecture. Now, I've been kind of sharing with folks that I think that Mars sample return is the grandest architecture that we have pursued since Apollo. These are going to return samples that are going to revolutionize our understanding not only of Mars, but of all of the inner rocky planets, sort of how these planets evolve. And it's going to give us so much more insight into sort of our place on Earth within our solar system and our galaxy. So with sort of this primer to our missions, what I want to do is jump into some of the highlights and findings from the Mars Science Lab, so the Curiosity rover mission. And so what I'd like to start out with is a little spec sheet here of what Curiosity has done. So we launched in November 2011, landed in August 2012. Our prime mission was 1 Martian year. We are now about 5 Martian years in, so that is more than 10 Earth years. And I have our Sol number here. I updated this morning, 3,639. So a Sol is a Martian day. So we have greatly exceeded our prime mission, and we're in our 4th extended mission now. So we're still exploring, we're still doing science. And we've traversed about 18 miles or almost 30 kilometers at this point, climbing up a feature called Mount Sharp. So let me tell you a little bit about the Curiosity mission. So it's not searching for evidence of life, it's looking for what we call habitable environments. So a place where life would want to live if it were there. So what we can do is look for aspects that a biological environment we want to live in, like evidence for water in the past, evidence for organic carbon, energy sources that like a little microbe, like a bacterium would want to use. We're also characterizing the geologic and geochemical environment of this stack of about 5 kilometers of sediments that are recording this really interesting sort of cross-section into Martian history. This ties in with exploring sort of larger scale planetary processes and something I'll talk about in a minute, which is the global desiccation of Mars. Mars used to have water and now it doesn't. Why? Where'd that water go? And what does that mean for the planet's evolution? And then lastly, we're always interested in what's it going to take to send humans to explore? What's it take to send humans to Mars? And so understanding our surface radiation environment is one of the things that we need to do to be able to protect our astronauts. So let's back out a little bit and let me show you where we are. So this is a map of Mars. Gale Crater is over here on our right-hand side, right at the Martian dichotomy here between the southern highlands and the northern lowlands. So this is a high-rise image of Mount Sharp, what's formerly named Aeolus Mons. And if we zoom in up here on sort of the northern extent, what we see is this is the mountain. It's about 5 kilometers high. And coming into the crater here, we see these channels carved into the surface. This is evidence that water was flowing into this crater and actually forming a lake system. And so that's what all of this blue is meant to show you. Where would water accumulate if there were water in this crater? And so these are the types of environments that we want to explore with the Curiosity rover. And so one of the really compelling parts about Gale Crater and this particular stack of sediments is that these rocks in Aeolus Mons record this dramatic shift from one with abundant water to the far drier climate that we're familiar with today. And so I'll show you some of our incredible images from Gale Crater here in just a moment. So let's zoom out and talk about what it takes to get effectively like a PT Cruiser-sized vehicle onto the surface of Mars. You can't land it with airbags like we did with the Mars exploration rovers. It's far too large. What you need is what's called the Sky Crane. And so this is a rocket pack on the back of your rover. And it had never been tested before. It had kind of gone from, let's try dropping something off of a helicopter and see if the radar works to see when we're close to the ground. But you can't take it from start to finish because we can't approximate what's on the atmospheric density and the time of entry and all of that. So this 1-ton rover had to use this rocket pack to land, and we couldn't test it from start to finish. So when it actually worked, this is the response of everyone seeing for the first time this thing autonomously landing on Mars. And so you also have basically a 7-minute delay where it's either landed or it's crashed. You don't know, and you're just seeing the data coming back. And so 7 minutes after it landed is when you see Adam Stelzner here, like really cheering, and this guy in the back who's just, that would be me. I would behave that way. So that's what it takes to land a vehicle of this size on Mars. So now what can we do with such a robust instrument suite on board the rover? Well, what we want to do, like I said, is characterize a habitable environment, one where life wants to live. And so what makes an environment habitable? So one of the first things I want to show you is this massive panorama that we took of one of the first places we explored on Mars, which is the John Klein area. And so in the distance there, that mountain, that is Mount Sharp. And so what we did, if you picture that previous map that showed where the water would be, we went down to the lowest possible point we could access. So if there was water, that was the last place it would have sat before it kind of evaporated away. And so this environment, although it looks like this, dry, cold desert today, we actually think in the past it looked more like this. Sort of these ephemeral lakes drying up. There's going to be some salts that precipitate, but we actually found that this environment had pretty circumneutral water. So like actually a pretty quiescent place. So what does it take to make an environment habitable? You need persistent liquid water. You need the key chemical ingredients that life requires. That's carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. And then you need a source of energy for metabolism. So on Earth, a lot of that is driven by sunlight. We don't think that actually probably took hold on Mars for a variety of reasons. So we're actually looking for little chemical reactions that microbes could do with rocks and minerals to drive their metabolism. So let's zoom into John Klein here. And I just want to point out this image. I feel like it's been out there for so long. This was our very first drill into the rock surface on Mars. In this particular site we called Yellowknife Bay. And what was really striking was that the red planet Mars is only millimeters thick. Once you get down beneath that red veneer, we see this beautiful reduced gray rock. So this is probably what the rock has looked like for billions of years. It's been preserved in that state. And the red veneer that we see is sort of just a really thin skin of oxidized iron on the surface. So now there's basically this entire different Martian environment just below the subsurface that now we can start to explore. And so what we found is that this particular site, 7 months into this mission, actually has all of the key ingredients for a habitable environment where microbial life like bacteria would want to live. We had evidence that we were at the end of an ancient river system that fed into a lake. That lake chemistry was pretty mild, not too saline, a place that almost anything could probably live in if it were there. All of those key chemicals for life have been detected in the rocks. And we found minerals in different phases that can actually provide an energy source to microbes if they were present in the past. So we finally seen this habitable environment that we were searching for just a few months into the mission. So this is starting to lead us to understand there's probably habitable environments all over Mars. This is really changing the story of what we think life could have been like there if it ever arose. So let's back out a bit and let's talk about what we have discovered. And this is just my attempt to summarize 10 years of science in one slide. So of course, the evidence for persistent past liquid water. One of the really beautiful things we saw right when we landed was this type of rock called a conglomerate. Here, okay. So a conglomerate, which is, you can see those pebbles in the rock. It takes a decent flow of water to move pebbles, right? And so we're looking at something that's probably like ankle to knee deep water flowing and moving these rocks, depositing them, and they get cemented in place there and stayed for billions of years. And we were able to discover them right at our landing site. We found a suitable environment for microbial life in almost every one of our drill holes that we have with the Curiosity rover. And we're only looking about 6 centimeters into the subsurface. So, it's not a lot, but imagine it's a world away from only looking at that surface. It's an entirely different sub-environment we can finally access. One of the key things that I study is finding evidence for organic carbon preserved in those rocks. Now, that doesn't mean it's evidence for life. It just means those building blocks are there. And we found evidence for a persistent and dynamic activity of methane in Mars's atmosphere. Now, this is one of the things that people say could be a biosignature. We found that it just doesn't follow, very basic models for abiotic or biotic generation of methane. So we're still trying to understand, where is this coming from? Why is it so different from what we would expect on Earth and from models of how methane should be behaving? We've also been assessing those radiation risks to humans going to Mars by monitoring over the course of 10 years. And we found that there was, in the past, a much thicker atmosphere with a lot more water vapor. And so there's this really great, it's just a few images, but basically just clouds on Mars. You can almost pretend that you're watching, the sun setting and you see some clouds going overhead anywhere you've ever been on Earth. So a really, terrestrial world in so many ways, but on a totally alien planet. So that's what we've discovered, but what are we doing now? So this is one of my most favorite images from Mars. So this is kind of a zoom up of Mount Sharp. We are now, somewhere in here, up into these beautiful layered sulfates. And, there's still kilometers of material to explore. And so I just want to catch you up with where we are. So we're going to zoom in to this region here. And I've used some colors to denote sort of different geologic units. So what we're transitioning into, and so this white line is showing you the route of the rover. What we've done is go from this environment that we know was wetter in the past because there are all these clays that are only deposited when you have water flowing in and depositing these really tiny sediments like clays. And then as you move up the mountain, we move into the sulfate-bearing unit, which indicates a drier environment where salts are basically precipitating out of evaporating water. We actually get these really beautiful structures like this little sulfate flower. I put it into quotation marks because of course it's not a flower, but it's this efflorescent salt that sort of bloomed out of the ground from the salts precipitating together. And so these just like really beautiful indications that we've experienced a really dramatic environmental transition on Mars. And so the little marker here shows you where we are. We've just transitioned up into the sulfate-bearing unit. We're starting to explore what is it that makes this difference between the Mars that had more water, could make all of those clays deposit, to the Mars that we're exploring now that's much, much drier and all of that water has evaporated away. So that is my briefest summary of Curiosity, what we're doing with that mission, and our ascent of Mount Sharp, of course, continues. So there's always news coming out on what we've seen more recently. So just keep your eye out on just like any media outlet. They're going to talk about what we're doing on Mars. So what I do want to do now is move over to talking about the Perseverance mission. So Perseverance, like I said, is the first step in the Mars sample return architecture. So some of the specs for Perseverance launched in 2020, landed in 2021. So we've got about 13,000 meters. So we are really trucking. We've collected 14 rock cores so far. Our prime mission is meant to be 1 Martian year, so we're actually still within that prime mission. And we're on Sol 606. So I just updated that. So that's I think our tactical Sol today. So Perseverance is doing things a little bit differently than Curiosity. And so some of those things are, we're still exploring the geology like we were with Curiosity, but with a little bit of a different purpose, and especially in the collection of our samples. So we want to understand the geology of Mars. We're collecting samples that we can do all kinds of experiments with. How old are these rocks? What are they actually made of? What are these minerals that are common on Mars but rare on Earth because of that dramatic environmental difference? But we're also interested in, of course, was there ever life on Mars? And so this mission is meant to look in a specific region that if there were life, there's the very strong possibility it could have been preserved in the rock record. And this is an example of that I'm showing here. Basically, a microbial mat that's been preserved in the rock record is something we call a stromatolite. We're collecting these samples and caching them for eventual return to Earth. And then, of course, we always have that component of how are we going to send humans to Mars? And so we have a couple of technology demos that flew with Perseverance that are helping us prepare for eventual humans to Mars. So let's talk again about where we are. So we've scooted over a little bit from Gale up here to Jezero, still on the Martian kind of equatorial region along the dichotomy here. So let's zoom in to Jezero. So this is Jezero crater. Here's the crater outline. And there's this interesting feature over here on the left. And this circle indicates sort of our landing ellipse where we are hoping to be able to land. So if we zoom in and let's get a higher resolution image, this is what's called a delta. So it almost looks like the Greek letter delta, right? And it's formed in a very specific way when water from a river is flowing into a lake. So we know that there was water carrying these sediments and depositing them into a lake in this crater at some point in the ancient Martian past. And so although it looks like this today, we think that that entire crater actually looked more like this in the past. Water flowing in and building, a subaqueous delta right here underneath the water, filling up the crater with water, and then maybe an outflow channel where some of that is exiting. And so that's what we're kind of looking for in the past. So let's zoom in here and see what we were able to accomplish with Perseverance. So just remember that, we tested out the sky crane when we landed Curiosity. So we felt fairly confident we would be able to do it again. And so our first entry, descent, and landing for Perseverance actually leveraged some new technology that's going to make it even easier for us to land with pinpoint precision. So this is EDL, entry, descent, and landing 2.0, where we take descent photos as we're landing. We compare it to an orbital map on board the rover, and we're able to divert where we land. So if we see a place that we really shouldn't land there, it's going to be really tough on our wheels, it's going to have rough terrain, we could actually have the computer auto nav itself to land in a good place. And so I didn't want to make this too busy with too many images, but one of the things it turns out you can do on a $2.5 billion rover mission is attach a bunch of GoPros to it so you can watch us land. And so there are plenty of resources online. I highly encourage you, if you haven't seen these, to go online and just find a landing video, because it really does look like aliens landing. We are the aliens this time, especially the sky crane here is the rover. So this is the rover dropping off the sky crane going towards the ground, which is the bottom image. And once it detaches and sky crane flies away, it really just looks like an alien spaceship just doing it's incredible. So documenting this, we knew it was successful, but documenting it was just brings that extra level of reality to it. So we land the mission. What are some of the things that we have on this rover we didn't have on the previous one? Well, one of them is our Ingenuity helicopter. So just like Sojourner, the rover, was a technology demonstration on the Pathfinder mission, Ingenuity here has been our tech demo helicopter for this mission. So our demonstration was to prove that we could have powered controlled flight on another world for the first time. Here's this great video of the helicopter. We're just doing an up and down test flight. And then we did 5 test flights to see, how is it for us to actually fly, take some images. So we've actually done, I think, 33 flights now. So once we exited our tech demo, we're actually in an operations demonstration phase to see how future rovers and their aerial explorers can work together to accomplish more science and more exploration with these relatively small vehicles. So that's one of the new things that we have. The other thing that we can do now is coring rocks, not just drilling down into the rock and making a powder, but grabbing samples that we can return to Earth. So I've got 2 images here. The top one is actually an abrasion bit. So it's meant to kind of just pound into the rock and get rid of that oxidized veneer that you saw before so that we can see what the texture inside the rock looks like. The bottom one is actually one of our drill bits. And so what we're doing is this cylindrical drill bit is going to cut the rock out from, the core out from the rock interior, collected directly into a clean sample tube. So there's a rock in the drill bit, and this is what one of our sample tubes looks like. Within that, very fancy tube, the core is going to be about 1/2 inch in diameter, about 2.5 inches long. So these are very expensive, small pieces of rock that are, in my opinion, going to be one of the most scientifically important samples that we can possibly bring back to Earth. And so this is actually what's called the cache cam. So we're creating a cache of samples, showing the rock inside the tube and then getting the hermetic seal on it so that we know that it is sealed and safe for caching and eventual return to Earth. So those are the new things that we've been able to do with Perseverance. And so what I want to do is just talk a bit about the science that we've seen on the crater floor and then going up towards that delta feature that I showed you. So on the crater floor here, so you can see sort of the delta that I pointed out to you, and our landing site's actually down here. We named it the Octavia E. Butler landing site. And if I zoom in and kind of show you our traverse, so we landed up here, and even though we wanted to go to the delta, which is sort of off the map now, what we want to do first was actually see what is this weird thing that we landed right next to, these 2 rock units. So we named them Maz and Seta, and we actually kind of bounced around the edge of it to get down into Seta. And so what we saw as we drove around the corner here were these nice layered rocks. We're like, okay, this might be what you would expect to see in a lake bed on a crater floor on Mars. These like low-lying paver rocks. Coming around the corner, you're kind of seeing similar kinds of rocks and geometries. And we finally dropped down into this really interesting Seta region. And so what we're seeing here, you see these like big grains. I know we don't have a scale bar on here, but these big green grains, and you can see them even in this image of an entire rock face. These are olivine. Olivine is a mineral that we see in basically igneous rocks, so rocks made by magmas cooling off. So it turns out in this lake bed that we meant to land in, we actually landed on a bunch of magmatic and volcanic rocks. So all of the rock out here, all of these are lava flows. And this is actually what we call an olivine cumulate, so a rock that only forms when you have magma cooling underground. So not what we expected, and I think that just tells us more that Mars is hard. There's so much going on that at the 50,000 foot view, you really can't tell those details until you get your wheels on the ground. So just as a summary of what we found in the crater floor, and here's that same loop I was showing you, what we've done is we've collected samples from 4 locations. So we took 2 cores at each of these sites. So you're going to have 2, 2, 2, and 2. And then the kind of third image that you see over here, these are all abrasions. Remember that abrading bit I showed you, which lets us look underneath that surface veneer and kind of get at the texture and try to understand what these rocks are made of before we take the samples. So we've got these samples. They're going to go from our sample return, but there's so much more that we want to explore before we're ready to cache these samples. And so that leads us to the Jezero Delta. So again, river deltas are habitable environments on Earth. That's why we want to explore them on Mars. And the Jezero River Delta specifically is really compelling because it has, from orbit, we can tell the signature of what we call smectite. It's a kind of clay. And those particular clays are really, really good at preserving organic matter and organic carbon. So if there was a biosphere and it made all of this organic carbon, it might be preserved in those types of minerals in the delta. That's why we want to go there. And so what we've done is, from that landing site, we kind of looped back around Seta and went up to the delta. And so let me just zoom in on that region of the delta. So this is it's a little fuzzy here, sorry, but the delta front, and there's a couple of features I can point out to you, really beautiful high resolution images from our cameras on board the rover. So this one is actually looking kind of north and off the screen at the delta. This is the front of the delta. This is probably a little delta remnant. So not a volcano, even though it has sort of that distinct shape. This really neat feature here is what we call Kodiak. This is one of my most favorite images from the Perseverance mission. So this is a delta remnant, meaning it's part of that delta that had prograded out into the basin, and it's been eroded back over eons of time of wind abrasion on the surface of Mars. But you can still see like really clear geometries, like these flat-lying rocks, and then these ones that are tilted, and these flat-lying ones again. That only forms when you have a delta structure prograding into a lake. So it's like this most perfect evidence for what we thought we were going to see on Mars. So finally we're confirmed that what we thought we were going to see, we're seeing. We also, if we look at the delta front here, finally encountered our first sedimentary rocks at a place that we called Enchanted Lake, and that's where we're exploring right now. We've also looked at this other part of the delta front called Hawksbill Gap, and we found these really intriguing kind of light-toned sulfate cemented mudstones that have a really interesting organic signal in them. And so we've been able to sample these rocks for Mars sample return. So let me just bring up like our whole suite of samples that we are going to be caching at this first part of the mission. And then we're going to actually continue up the delta and out of the crater to collect several more samples. And so I think that we are able to return maybe up to 30, something along those lines. So we're going to have 2 caches that we can choose from to put our samples in to eventually return to Earth. And so the samples that are new, once we got out of the crater floor over here on the bottom right, the new samples are all up here. So Shuyak and Mugik, Hazeltop and Bear Wallow, and Swift Run and Skyland are all cores coming from the delta front. So let me just step back from what we're collecting with Perseverance right now to what we intend to do with them, with Mars sample return. So hopefully what you've gotten from this is kind of the last decade of Mars exploration focused on what our rovers have been doing, although of course there are other missions from other space agencies. We have landers that have done incredible science in the past decade. Really the next decade of Mars exploration is Mars sample return. So this is going to include Perseverance collecting samples. We're actually sending some helicopters to help with collecting those samples and sending them to the Mars Ascent Vehicle. This is going to be the first time that we launch off the surface of another world. Just like with Sky Crane, a technology that can't be demonstrated start to finish until you're actually on the ground and ready to do it. But this is that grand architecture that's going to enable us to bring back samples that are going to inform us in ways that we just cannot possibly do with robotic exploration alone. And so that's sort of the next stage, next step in Mars exploration. And so with all of this, I just want to say, we have these incredible questions that we are finally able to answer. We have so many more places we can go with Mars and planetary exploration. And one of the motivations that I have for this, I want to share with you, one of my favorite quotes from Carl Sagan, that the universe is a pretty big place. And if it's just us, it seems like an awful waste of space. So with that, thank you so much.
Well, thank you very much, Dr. Williams. That was really fascinating. Do we have any questions from the audience? Yep.
Do you want me to exit it?
Hi, That was very interesting. Thank you. What are you doing to prevent contamination?
Yeah.
Because it seems like, particularly with humans going up there, it's almost inevitable.
So yeah, it definitely depends on who you talk to about the potential for humans to forward contaminate Mars. Certainly a concern for many people. So there's an advisory body. Oh, see, this is like, sorry, side camera. You were looking at my back the whole time. There is an advisory board or group called COSPAR. One of the things that they developed years ago, decades ago even, is policies on forward and backward contamination potential from any world we go to. And Mars, you know, and the icy outer ocean worlds are ones that are focused on a lot. And so when we send spacecraft, we go through all of these steps to sterilize everything that goes into the spacecraft as well as the exterior. They are never going to be totally and completely clean, right? So the metric, and don't quote me on the actual number, but the metric is some 1 or 2 like vegetative spores on the entire spacecraft, which are allowed to travel. And presumably, so long as you don't give them a habitable environment to take advantage of, they ought not to be able to reanimate and proliferate. And so that's been how things have handled for a while. And the level of cleanliness that has to be accomplished with like taking the cores and putting them in the drill stem and then hermetically sealing them, all of that is carefully worked out so that we are not forward contaminating. But then, you know, now there's the conversation of, well, you're about to bring samples back from Mars that you hope have evidence for ancient life, right? Not something modern that can reanimate, but that's the kind of, you know, Pandora's box you can't close, right? And so what's being built is a one of its kind facility that will house these samples upon their return. So all of the steps, so like launching off the surface of Mars, we're going to actually capture that rocket with an orbiter that brings it back to Earth. There's a detach of the sample vessel from the orbiter, so you have no direct contact with things that have touched Mars until you get to delivering that to Earth. And then it's going to go to this facility that nothing can get in and nothing can get out. And so it's an interesting way of kind of building a facility that keeps outside contamination out and keeps anything inside in. So it's always this balance of forward and backward contamination, and depending on who you speak with and the studies that they are citing, you know, there's the concern about whether the human microbiome could proliferate on Mars if it gets, I mean, like the surface environment is sterilizing, right? The radiation flux is enormous. But we do see organic molecules, right? And those should all be destroyed by those fluxes. So if there is a way to preserve the organics, maybe there's a way to preserve life. There's a really interesting study came out a few days ago about radiodurans, Deinococcus radiodurans, which is the organism that they see in like nuclear reactors that can repair its DNA. So I think that our understanding of extreme environments, which I know is our topic for today, is really evolving, and how life adapts to those environments. So you're not the only one to think about it or be concerned about it or, you know, to plan for it, but it's certainly topmost priority to maintain those protocols from our sample return. So I saw one back here. Okay.
First, I want to say thank you and wow. You describe a lot of things that seem very Earth-like to me. The scene you showed with the mountains in the background, and then you had part of it colored yellow. To me, it looked like the layers, which means water laid down sediment, and then I'm not a geologist, but if I tried to play it,
you know, you're playing one well on TV.
It seemed like it was laid down in water, and then it was uplifted, and then it was eroded, and I presume by water, since the atmosphere is so thin and atmospheric erosion was probably pretty small. Is that a correct or close interpretation?
Until you got to the very end there, it was very, very, very close. Yeah. So the thing with Gale Crater that's so intriguing is that all of those sediments in Mount Sharp appear to be laid down from aqueous interactions, right? From lakes, from the evaporation of water, from rivers flowing in. I mean, it's, you know, 3 to 5 kilometers of sediments that are exposed. That's an enormous amount of material. there's such a discussion about why that central peak is there. So did it form from the original impact that formed the crater, where you would have a central peak? And so if you have sediments laying down on top of it, perhaps they're building on that pre-existing geometry. But when you look at the whole crater and the sediments on the outside, you can actually see where some of the sediments from the crater have topped over the crater rim. So it looks like it was almost filled in completely in the past. And then those materials have been basically winnowed out of the crater by aeolian erosion. And that's it's incredible, right? Because like the air pressure is low. So like, I was just talking with Paula about how The Martian is a really fun movie, but that the windstorms wouldn't really knock you over because of the atmospheric pressure. But if you have 3.5 billion years of wind just scouring, you can move an incredible amount of material. So yeah, you got really, really close. And I think without going to Gale Crater and exploring it the way we did, we may not have been able to come to those conclusions without, again, wheels on the ground. Thank you.
Yeah, and at lunch you were talking about too, the question about where did all the water go? Is that something you wanted to just recap a little bit? Because I thought that was pretty interesting.
A great discussion about this. Yeah, a lot of times I can prime someone. You want to ask me where'd all the water go, Amy? Well, the water that used to be on the surface of Mars was actually, it's been sort of, Mars has dried up because it did not have that thick atmosphere to protect it. And so the reason is because very early on in Mars's history, it's geodynamo. So that is the core rotating within the planet, creating a magnetic field that died off. So Mars is a much smaller planet than Earth. It's cooling off more quickly than Earth has. And so without a magnetic field, you can't protect, the planet can't be protected from like solar wind. So the solar wind was actually eroding away the existing atmosphere. And once you have less atmosphere, you have lower pressure, and you're not able to maintain what we call the triple point for water. So you can't keep liquid water stable on the surface. We know there's ice water. There's a little bit of humidity every once in a while in the form of water vapor, but liquid water is extremely transient. And so that's, the water has just been either stored in hydrated minerals, lost to space over the course of geologic time. And that's what leads to it being, this dry, cold desert now, where we knew it had abundant water in the past. Okay, sorry to interrupt your question.
I was going to ask, are you there?
Yeah.
I was going to ask you where the water went, but I also noticed that it appears that those sediments have layers, which implies some seasonality that causes a lot to be deposited and then very little, and then a lot, and then a little. Is there any hypothesis as to how that, what's causing that?
Right. So it's less seasonal and more periods of like long-term deposition. So if you have water coming in from outside the crater and into that crater floor, so water is going to flow downhill even on Mars with lower gravity. And so if that water is carrying sediment, it's going to flow in and it's going to form those layers. Sometimes we see, so varves are the term that describe that very, very thin seasonality layering. And sometimes we see things that we wonder if they are varves, like a wet year and a dry year, whatever, or just seasons like that. And while we're not convinced that's necessarily what we've seen, because again, like to establish that on Earth, you would use techniques that are simply not available to us on the rover. So you don't want to say, conclusively, clearly these are seasonal varves, but man, some of them sure do look like it. Now that larger scale, like layering that you're describing, that is, 1 billion years of sediments flowing into this basin and forming this massive stack of rocks. Yeah. Great question. Thank you.
I've got one more question.
Yeah.
So what do we know about any ancient biological life on Mars? And what are the initiatives for that?
Yeah, great questions. I mean, the question is always, are we alone in the universe, right? And so with Mars having started out very similarly to Earth, right? So the inner rocky planets all formed at the same time in solar system accretion and formation. It had water on the surface at the same time Earth did very early on, and it had water at the time that life arose on Earth. So the question is, did it arise on Mars? Did it not? And why? What conditions could make our world so different that early on? So, if we're looking for life on Mars, we can look on the surface. We haven't seen it there yet. We can look in the subsurface, but we're limited by how deeply we can drill. As you saw, 6 centimeters, right, is as great as it was and is right now. Now, there are future missions that are looking to drill 2 meters down into the subsurface. So the European Space Agency's ExoMars mission, which is suspended and hopefully going to launch in 28, was meant to look for evidence of ancient life as well. And there's actually a new mission that was just recently prioritized by the Decadal Survey for Planetary Science and Astrobiology called Mars Life Explorer. So this is a mission with a 2-meter drill that's actually meant to go to regions where we see water ice within the first meter of the subsurface. It's meant to drill down into that and collect samples to analyze for evidence of a modern biosphere. And I'm totally tooting my own horn here because I was the science champion for that mission that the Decadal prioritized. So after Mars sample return winds down and that incredible spending that it does cost to do such incredible science winds down, hopefully the next mid-class mission to Mars is going to be a Mars Life Explorer.
Okay, and the samples that you were showing that have been collected, I was a little confused. So what are we doing with those? So we're not bringing those back, or we are bringing those back?
So those are the samples slated for return with Mars sample return. So that's two additional missions that will launch in 28. I had 26 to 28 listed there because there's 2 launch windows. But the one that will land the ascent vehicle, where we'll put the cores into the ascent vehicle, it'll launch back up into Mars orbit, and then that orbiter will grab it and bring it back to Earth. So, and then we're making 2 caches, one pretty soon actually in the crater floor down in front of the delta, and then one that's going to have not only the duplicates of the samples that we collected, but then everything else we collect from the top of the delta and the crater rim and out beyond Jezero crater. And so we're going to have this incredible suite of really ancient rocks, and some of which, if there was evidence for life on Mars, these are the kinds of places you ought to be looking for it to be preserved. So yeah, those are going to be the 2 caches, and we'll return one of them in the 2033, I think, is our date for return.
Terrific. Okay. Oh, a few more questions.
Yeah, of course.
Coming over. Let me get Ray first, then I'll come back.
So COVID didn't. Every launch I feel like is always delayed. I think this was supposed to be 2018 and it launched in 2020. I think Curiosity was supposed to be 2009 and launched in 2011. So things always kind of slip.
Thank you for your talk today. It's very interesting. Are there other countries that are doing the same thing we're doing? And if so, is there a collaboration and all of that?
Oh, that's a really great question. Yeah. So the European Space Agency, of course, has been sending missions to Mars and collaborating with NASA for a while. Mars Sample Return is actually a collaboration between ESA and NASA. There is the Russian Space Agency that has been working with ESA as well for a while. And then there's actually, so the Chinese Space Agency, of course, is active, and both the Chinese Space Agency, which landed a rover on Mars just a little bit before Perseverance landed, and then also the United Arab Emirates sent an orbiter to Mars called the HOPE mission. And so these are, I mean, there are other space agencies, of course, but these are the ones that have been active on Mars recently. And so, yeah, there is collaboration on different projects between space agencies. All of the data collected by NASA missions is posted to a planetary data system, hub basically, or node that shares it, globally, right? So anyone can access these data and do science with it. We just take like a 3-month embargo so that those of us doing day-to-day rover operations have a chance to look at the data and also say something about the science before we give it to everybody else. Just because day-to-day rover operations take so much effort. It's a full-time job. And I don't know how some people do way more than I do just as a university professor, and I have grad students, but I'm also working on 2 Mars missions. it is a full-time job in and of itself. So more than you asked for, but hopefully that addresses it.
Can I ask, I'd like to ask two questions. One simpler and one much harder, I think.
Ooh.
The 6 centimeter cores you get, are you able to age them or not until you get them?
When you get them back, yes. So
Okay.
caveat to that, on the Curiosity mission, for a little while, we had the capability to do basically exposure ages, so we could see how long something was exposed to basically the radiation environment. And so we were getting ages like some of these rocks on the order of billions of years, which is what we expected. But to get, the error bars on that were large, reasonably so for a mission that wasn't supposed to be even able to do that. But bringing these samples back to do very precise, absolute dating on them, we're finally going to have bracket ages for when there was water on Mars. Something that is like, we wave our hands in the hundreds of millions of years, right? But like, you're going to have a date. It's incredible.
That's great. Can you, once you know the age of that, and it seems like what you were describing as a former situation on Mars sounds very Earth-like, but it's gone through a process of aging and losing atmosphere and radiation. Do we expect the Earth to go through something like that? Can you project back, if you can project back a couple billion years on Mars, what does Earth look like a couple billion years from now?
Ahead. Yeah, so as a geologist, we think about what Earth has been like over the 4.5 billion years that it's been around. We've got another probably about 5 billion before the sun consumes the Earth, so we have time. So when you think about continents forming and then moving around the world due to plate tectonics, right? You have all of these different processes on Earth that actually aren't really mimicked on Mars. So Mars being a smaller world, if plate tectonics existed, it was very early on. And when the geodynamo kind of failed, that also would have basically ended the convection that would allow plate tectonics to occur as well. So many of those like interior planetary processes that we're starting to think are actually key to habitability, at least from the Earth perspective for life as we know it. Those things just didn't seem to stick around for very long on Mars. So, I mean, yes, but not on a time scale that's not gonna matter to humans, and really isn't gonna matter to Earth before we get many more billions of years down the road. So we're slowly losing heat, right? Thermodynamics is still in play even on large worlds, and so we're losing heat. So our geodynamo is gonna slow down and has slowed down since Earth first formed. But on the order of geologic timescales, it's not going to impact us so much. But yeah, you're going to see that slowing down. Plates are going to keep kind of circulating and bumping into each other, forming mountains. All of those processes will continue. Thanks.
I just wanted to ask why the southern polar cap is so much bigger than the northern polar cap.
Oh gosh, where no, right? You have to go to something that's so far outside of my expertise.
Okay.
I'm gonna, you can pass it back. Say planetary dynamics. I'm gonna wave my hands a lot at that. I know. Now I'm gonna feel like a failure. I'm gonna go look it up for you.
Okay, I think we have time for one more question and we'll let you go.
Yeah.
So you brought up aging. How are you going to do that? Is carbon-13?
No, so carbon-14 dating is only
14.
Well, so that's only good for like tens of, maybe it's just thousands of years.
Oh.
No, so you use, there are a lot of radiogenic isotope systems that go way, way back. So you're talking on the order of, it's radiogenic isotopes. Yeah, carbon-14 is a radiogenic isotope, but systems have different time periods that they are effective for. So like uranium lead would be one that can get way back in the geologic record. Yeah.
Okay, well, please help me thank Dr. Williams again for a great lecture.
Thank you so much.
And please join us next week. We'll have our final lecture from Joe Ryan from the Whitney Lab, who's going to be talking to us about the fascinating world of jellyfish. So see you all next week.